Okay, we have another problem to work here. Problem's over here in blue, and then we'll put our solution over here in black. Okay, suppose carrier heating and cooling is discontinued in one of their furnaces because its combustion efficiency is too low, at best 70%. A new model is chosen to replace the old model. Efficiency measurements were recorded from the new model for 10 furnaces. The sample mean and standard deviation were found to be 71.3 and 2.74 respectively. Do these results provide strong evidence that the average efficiency of the new model is higher than 70? Test that alpha equals 0.05 and assume the distribution is normal. Okay, so we got to come up with our null and alternate hypothesis. Well, here's the old furnace, and here is the new furnace. What do they say about the old furnace? Not good enough. What about the new furnace? We hope it's better. You follow that? Okay, so what was the old furnace? At best, 70% efficient. We want this new model to be more than 70% efficient. We want to have an improvement. We want a significant, statistically significant improvement. Okay, so what kind of test are we going to do here? Well, let's get out our old flowchart here. Is n greater than 30? No. Is the data approximately normal? Yes. Is sigma known? We are told we have the standard deviation. Are we told we have the population standard deviation? We're not told the word population is not in here. Also, the symbol sigma is not here. We cannot assume that we have, here's reality. Sigma is a better value to use than S, the sample standard deviation. However, do we know that we have population standard deviation? No. So therefore, we can't automatically assume this is population standard deviation. We have to assume it's sample standard deviation unless told otherwise. So that says, is sigma known? No. T-test. So this is going to be a t-test right here. Okay, and I can look from this right here tells me what tail it is, whether it's upper or lower. We're looking in the upper part. Alpha, they have a 0.05. Now, degrees of freedom is not infinity. This is not a z-test, so the degrees of freedom are not infinity. If you remember, the degrees of freedom are n minus 1. N is 10. 10 minus 1 is 9. Reject if t. This is a one-tail test, and I did not write that up here, did I? One tail, I need to write that. One-tail test, so those symbols match. And now I'm going to use these two numbers right here, my alpha and my degrees of freedom, to find my t critical value. Alpha is 0.05, which is right there. And then I go down here to 9. And I find the intersection that is right in that area there. If I look at it closely, I get 1.833. That's 1.833 right there. Okay, now we can make this computation. As I've said earlier, this number always goes here. Our sample value goes first. Standard deviation divided by the square root of our sample size. Okay, type that in. Ooh, 1.5. 1.5 is what I got. So where does 1.5 land? And I'm going to put this in red. It is not in the rejection region. 1.5 is not. So what do? We failed to reject the null hypothesis. There was not evidence to accept H1 is true. Well, there's a t-test. I will put up a couple more problems, and then we'll be finished with chapter 8.